So we have a figure here, kind of like a four-pointed star, if you will. And the question's asking what transformations can be used to map the figure onto itself. And so what that's really saying is, what can I do to this? What reflections or translations or rotations can I do to this thing? And then after I do it, it looks like I didn't do anything, right? So for instance, is there a way that I could rotate this so that when I'm done with the rotation, it looks exactly like it does now? Or is there a way I could flip this, a reflection, that would make it look exactly like it does now? Translations or slides, that seems like it's not going to work, right? Because if I slide it somewhere, the shape doesn't look any different, but it's in a new location. And that means it didn't map it onto itself. It mapped it to a new location. So the translation part doesn't seem like it's going to work. So that's the idea that we're going to be looking at in this video, is how can we take a shape and do it some kind of transformation, but it looks like we didn't actually do anything to it. And if we can do that, it means our shape has symmetry. So a figure has symmetry if some rigid motion can map the figure onto itself, like I was just describing. Reflectional symmetry is probably the one that we are most used to. Reflectional symmetry means that we can reflect a figure onto itself. This is the kind of symmetry that I think most people are probably used to. When you saw the title of the video was about symmetry, you probably already had an idea about this kind of symmetry. Some people think of it as, can you fold the shape? And when you fold it, the two parts will match up perfectly nice with one another. It won't be anything like kind of hanging over. And so for this particular shape, we can see here two lines where if we reflected the shape across those lines, it would look like we didn't do anything at all. So if we reflected across this vertical line M, this point here would flop and go over here, this point would go to that point, this point would go over here, and that point would go over there, and it would look like we didn't do anything to it. Or if you can imagine, again, folding this shape along that line, the two parts would match up perfectly. So it has this vertical line of symmetry here. But then there's this one here that also would work, because if we reflected the shape across this horizontal line, again, this point would flip down to here, and this point would flip up to there, and same thing would happen with these 2 points over here, and everything would just kind of look like nothing had happened. Or, again, if you think about folding this along this line, all the parts would match up perfectly. All the edges would kind of match up to each other perfectly. So those two reflections map the figure onto itself, and each of those lines is called a line of symmetry. It does say, hey, look at this. Notice the fact that lines M and N both divide the figure into two pieces with the exact same size and shape. That's another way you can tell whether something might be or might not be a line of symmetry. Does it divide the figure into two identical pieces? Because if not, then it can't be a line of symmetry. Now, rotational symmetry is where we can take a shape and we can rotate it less than 360 degrees, and it'll look like we hadn't rotated it at all. And the reason why we say less than 360 degrees is because if you think about rotating any shape 360 degrees, it's going to look identical to when it started, right? Because a rotation of 360 degrees just means spinning the whole thing back around and getting back to where you started. So in this shape here, if I rotated it 90 degrees, that wouldn't work. Because if I rotated this shape 90 degrees around this like kind of center point here, then instead of being kind of oriented long ways here, it would flip-flop, and it would, we can kind of sketch it out. If I rotated this thing 90 degrees, it would maybe look a little bit more like this, right? And so it doesn't look like it did when it started. But if I rotated 180 degrees, then that means that it's going to, this point here is going to spin all the way around to here, and this point here is going to spin all the way around to there, and it's going to end up looking just like it does now. So the rotation of 180 degrees around point P maps this figure onto itself. So we say it has rotational symmetry of a rotation of 180 degrees. So here we have a question that asks, how many lines of symmetry does a regular hexagon have? And a regular polygon, like a regular hexagon or a regular pentagon, means that all the sides are congruent and all the angles are congruent. So this is a regular hexagon because all of these sides are going to be the same length, all these angles inside my hexagon are going to be the same measure. And so the question is, how many lines of symmetry would this thing have? How many lines could I reflect it across, and then after I reflect it, it would look identical to the way it started? And another way to think about it is, how many ways can I divide this thing into two equal parts that are the same size and the same shape? And if I look at this, I notice that, hey, I think if I just folded this thing with a vertical line going straight down the middle, that would seem to be a line of symmetry. So let's sketch that one onto there. Let's put that vertical line on there. That seems to be one line of symmetry. We'll call that line A. But then it seems like I could also do that going through the midpoint of any of these sides, kind of doing like a perpendicular bisector of any side, right? I did a perpendicular bisector of like the top and the bottom, and that turned into a line of symmetry. But will it also work if I do like the perpendicular bisector of this side, or these two sides? Yeah, it kind of seems like it does. So maybe that's another line of symmetry. And then if I have the two remaining sides here, if I go through those, seems like another line of symmetry. But are we done? Is that all that we have for lines of symmetry in this shape? What if we go through the corners? So let's look at those. I'm going to kind of maybe do these in another color. I'll do these in black. If I go through from this corner to its opposite corner, that seems like it's another line of symmetry. It's dividing my shape into two equal parts that are identical. If I folded this part along this line and folded it up to meet over here, all the edges would meet up perfectly. So there's another line of symmetry. And then I can kind of go around the shape, and I can keep doing that going through opposing corners. So there's another one. And I can do it going through these opposing corners right here. So there's another one. So it appears that my regular hexagon in this case, has 6 lines of symmetry. Now I would challenge you, I'm not going to go through it, but I want you to think about, how could I rotate this shape? Well, how many different ways could I rotate this shape? And so it would have rotational symmetry. If I rotated it 90 degrees, for instance, would that map it onto itself? Or if I rotated it another number of degrees, would it map it onto itself? A question like that. Here we have a couple more questions where we're asked about lines of symmetry. And so I would, before I go through these answers, let's maybe take a minute and see if you can figure out how many lines of symmetry these two shapes would have. Let's start with the rectangle. If I look at this rectangle and I look at the sides of it, I kind of maybe notice that if I were to take this top and bottom and kind of split those down the middle, it appears that that would be one of my lines of symmetry, because that one, I didn't draw my line very straight there, but you get the idea, right? If I split it right through here the middle and I folded these over, they would appear to match up. And I think I could do the same thing folding it more horizontally through the middle like this. It would seem like the two sides would match up. But is that all? Because in the hexagon example, we could go through the corners. Let's think about that. What would happen if I folded it more through the corners here? Let me get my line tool out. Let me actually use my line tool here. So let's fold it through the corners. So I'm going to come right up through here. Is that a line of symmetry? Well, I do notice that it splits my rectangle into two parts that appear to be identical in size and shape. So it seems like maybe it is. But then if I think about actually folding this, taking this and folding it up here, this corner is not going to lay on top of this corner. When I fold this, what it's going to look like is it's going to look something more like this. Remember, when I do a reflection across this line, this point is going to go straight across to about right there, right? It's going to go straight across that line. And then if I connect that point to the other corners, then when I fold it, it's going to look more like this, right? It won't match up with these existing sides right here after I fold this side up over there. So I don't think that line there, I'm going to get rid of it, it's kind of gotten a little bit messy. I don't think that this line here, this turquoise line, that doesn't appear to be, to me, a line of symmetry, right? I think the only lines of symmetry we have in this picture are going to be, oops, I didn't mean to do that, are going to be the two yellow ones that I had there for a second. There we go, I got that to disappear. So my two lines of symmetry would just be these two. So it's going to have two lines of symmetry. How about my trapezoid over here? How many lines of symmetry do you think that has? Well, I do notice that if I were to fold it along this vertical line here, it seems like the two sides would match up. I don't think if I folded it along that line, I don't think that would work. Those don't seem like they would want to match up. And I don't think if I folded along these corners, that would work. I can tell right away that's not creating two shapes that are identical in size and shape. So I don't think corner to corner works there. I think the only line of symmetry for this one is the one that I have on the screen right there. It only has one line of symmetry. Okay, let's look at one more example where we're going to ask, does this shape have rotational symmetry? Remember, a rotational symmetry means that our figure can be mapped onto itself by a rotation of less than 360 degrees. So in other words, if I spin this thing, if I kind of pin it down, we'll say we pin it down right here in the center, we'll call that point P. If I spin that down pin that down right there and then spin it a certain number of degrees, so I spin all these sides around, will it end up looking just like it does now? Well, it kind of looks like the 4 points here are identical, so that we got that going for us, that these 4 points look to be identical. And I think if I just take that point here that's kind of pointing east, if you will, and I turn it so that it's pointing up here, I think my shape will be back the way it looks now, right? If I just turn it a little bit, if I were to just kind of sketch this out real quick, if I were to just turn it to where it was pointing this way, right, that would not work. Because if I just turn it that much, it's not mapped onto itself. So that rotation doesn't work. But if I were to rotate it to where this east-facing point points north, and the north-facing point points west, and the west-facing point points south, and so on, then that would work. And that would be a 90-degree rotation, right? I'm rotating it a quarter of the way around the circle. So it looks like it has 90-degree rotational symmetry. Right, 90 degrees seems to work. And then if I were to continue on and spin that thing all the way around to there, so that the east point is now on the west side, and the west side is on the east side, and the north side is on the south side, and the south side is on the north side. So I'm spinning everything around to where it's like in the opposite location. That would seem to be back to the way this started. And that would be a 180-degree rotation. So I'm looking at having 180 degrees of rotational symmetry. But then I can still, I think, rotate it from here all the way around to where now it's pointing down. This one that's pointing east, if I rotate it all the way around to where now it's pointing south, then the north one would rotate all the way around to where it's pointing east, and the west one would rotate all the way around to where it's pointing north, and the south one would rotate all the way around to where it's pointing west. That would rotate and bring us back to what it looks like now. And that's 3/4 of a total turn, so that is 270 degrees of rotation. 270 degrees of rotation. Now the second part of the question says, does the figure have point symmetry? And that's just a term meaning that it can be mapped onto itself by a rotation of 180 degrees. And yeah, we said that 180-degree rotation would work. So we would say that yes, it does have point symmetry.